start over from zero. Why is this thing blinking now? That's what I'm trying to understand.
I don't even know.
It was green. The upper one was green before. The lower one was red. Then I thought, okay, let's try to figure out if we can change this.
Oh, those ones are green.
Is it green? Red.
What is red versus red?
I have no idea. But it's a little yeah, so I changed this. Oh yeah? No, let's go back. This one was only 1 out of 3. Oh,
Okay.
Alright, should we try to plug in?
Yes. Okay.
So we'll start in a second. While Yuan and Ting are setting up the next talk, just a brief announcement. For dinner, I mean, everybody of you has this voucher, and I guess it's clear that this voucher is for the whole week. Should there be anybody who doesn't have a voucher yet, they can find me in my office, which is 5219 Chamberlain. You find it on the website. And I have some more vouchers in case somebody ran out or didn't come before. The other announcement is that there will be the lab tour. Today is Marcus Ming's lab. And I think, is it right? Chen, are you collecting everybody for the lab
Yes,
tour?
after this lecture, I will grab everyone and for the lab tour towards regarding qubits lab.
Perfect. All right, so these are the announcements. And then, without further ado, we can actually hand over to Yuan Ping. Yuan Ping is also affiliated to the physics department, but actually in engineering. She's a great expert for ab initio methods to describe quantum materials, and in particular also in the context of defects that we heard previously in Jen's talk. So, yeah. Stage is Yuan's as soon as it is ready to go. Oh. Perfect.
Okay. Great. What? Is there a pointer or something?
Just
Do we have a pointer?
Something? Continue to show where's the.
Oh, here.
Ah, okay.
do you have a pointer?
I have one.
Okay.
There. Okay, fine. It's okay. It's okay. Okay, so I'm Yuan Ping. I'm from Material Science Department and affiliated with physics for my research on first principle theory, method development, co-development for quantum materials. So quantum qubits. Qubits with quantum defects as the material object is part of my research. And I will give you some more specific example in this presentation. And you feel free to ask me questions and stop me if I'm going too fast. So I'll start with giving you some background, and then we'll talk a bit of the theory, and then give you specific example how we look at optical readout. So just start with the background for quantum information science, rely on fundamental principles, since we have a lot of talks today already. You already understand you rely on the fundamental principle of quantum superposition and quantum entanglement, where the quantum bits is the fundamental elements. building blocks. And in terms of application, we have various of applications in the device level of for quantum communication, quantum computing, and quantum sensing. So as a material scientist, we always worried about more material host, for example, for a host for spin qubit. So this type of qubit are using spin state as the fundamental information carrier. And one good thing about this type, it can operate at relatively higher temperature, much higher than the superconducting qubit. And you can use isolated defect, like impurity in solids, as the spin qubit object, or you can use, for example, quantum dot with one electron as a spin qubit. And in my research, I have been most focusing on this defect as a spin qubit, which is pretty broad. Many materials can be the host. For example, silicon carbide, diamond, or HBM. And you can implant in any kind of defects or impurities. For example, the NV center in diamond is a type with nitrogen substitution nearby a diamond vacancy, a carbon vacancy with one negative charge. I'm sure you have heard about it several times today, but that's not only one. There are also many other possibilities can be used as a spin qubit. I'm going to tell you a few more examples and how we do theory on this type of problem. So, what are the relevant material parameters for the application of spin qubit? We need three types of categories. We need to have efficient readout. A lot of spin qubit is using optical readout by input photon and output photon, and based on the photon energy and polarization and spin dependence to read the information of the qubit. And this diagram is the classical NV centers optical readout diagram with this cycle of intersystem crossing between triplet and singlet. I'm sure Jen has introduced this today already. She probably went through in detail. And this first one tells you which spin state your system is at by using optical readout. And you also want, if you have a spin state, you need to initialize it such, and you want it to be kept long enough time, or you want to manipulate it to a certain state, you want it to be kept, and you want it has relatively long lifetime comparing with the time of operation. So a lot of times, figure of merit of spin qubit is also it has long relaxation time T1 and decoherence time T2. So the distinction of these two, you can think of physical picture. The T1 is related to the spin polarization loss, like spin flip from up and down, and the T2 is more related to the phase information of the spin or the relationship between the different spin states. And we're not going to talk too much about it. This is a very important subject. And at the end, you want to have quantum information transduction being efficient, then the qubit can talk to each other. You can operate, for example, quantum computing. None of the current spin qubit candidates are considered ideal at this point for scalable quantum application. So we need to design new materials for spin qubit in quantum sensing or quantum computing applications. So even NV Central have been using so much, their optical property is not great. The optical ODMR contrast is about less than 30%. And you want it being as large as possible and have higher fidelity of the qubit. So that's what I wrote. You need a long coherence, an efficient readout, and efficient quantum translation. So when I mentioned about the optical readout, what is required for efficient readout from optical approach? Firstly, you want to have a qubit, good single photon emitters, which has an efficient emission of photon one at a time. So it needs to be optically addressable and very bright PL. And second, it has to have a high readout fidelity, which rely on the spin dependence. So you want to have your PL contrast has a spin dependence. Then you can clearly recognize which spin state your system is at currently. So what do people do if you have these two properties? Okay, this is showing. For NV-centric diamond, for example, if you all went through this once a day, I'm just going through this again. So the NV-centric diamond has its electronic structure such: your ground state is triplet, you have MS0 and MS plus minus 1 spin state being split. This is so-called zero field splitting. Without magnetic field, the MS state is already split. And you also have a triplet excited state, and they also have a splitting. Then you have also other two levels, singlet, so MS0, and they are so-called intermediate shelving state. We are using them for intersystem crossing. So what happened in this process is, okay, before I show this picture exactly, what happened in this process is you first have a photon in through optical excitation. You will have electron excite from the ground state to excited state. It can excite from MS plus minus 1 state. Most of the time it's a spin conserving process, so it's going to excite to plus minus 1 state 2, or MS0 as where population sits, then it can also excite to MS0 state. So when your photon in electron excite from ground state to excited state, and then it will go through intersystem crossing. This is done, but it's fine. It will go through intersystem crossing from the triplet state to singlet state, and this intersystem crossing can have different rates between MS plus minus 1 to singlet or MS0 to singlet. And these two rates need to be different. And if they are the same, it's not going to be able to recognize the difference between MS0 or MS plus minus 1. And then it goes through the singlet to singlet recombination, and then it will go backward, go back to the ground state, also through singlet triplet intersystem crossing. In the meantime, you also have recombination process. This is being conserved from, for example, MS plus minus 1 to plus minus 1 or 0 to 0. So you can see all these processes will happen at the same time while you are shining continuous light. And how you read out information. So if your population sits at MS plus minus 1 state, in NV center, this plus minus 1 to spin 1 a singlet state, the transition has a speed faster than the MS0 to the singlet state transition. And if the speed being different, what the resulting is the emitted photon number would be different. At the end, you will find the emitted photon has a different speed. So this is x-axis, is time after laser turn on, and you can see if electron sit at MS0 initially, and it will have the photon emission in this way. In this curve, if it's a ms plus 1 state was an initial state, they will have the black curve. And you'll be able to see the difference between the two curves clearly. So this is one type of readout. This is the transient spin-dependent PL contrast. So if these two curves are different enough, and then you will have a large enough contrast and have a higher fidelity. If these two curves will overlap, the readout is very low efficient. And mathematically, you can calculate the PL contrast, which will be the difference of excited state occupation N0 and N1. And the excited state occupation will be determined by the different kinetic rates. So from the calculation, you first need to calculate the kinetic rates, and you insert in the kinetic equation, and you can look at time-dependent occupation change, or you can look at the steady state occupation at a different state I. And that's how we look at it. At the end, well, this photon count N is related to the spin state ms. So underlying of this entire process, rely on you have these kinetic rates. It's making a difference between different spin sublevels. And of course, in the meantime, you want to have the photon out. So you have to make sure you have a process of this triplet to triplet, singlet to singlet. Singlet to singlet actually is non-radiative. The triplet to triplet has a loud transition, it has a photon out. And this green curve is actually non-radiative process. They don't have photon out. So that is the general idea. If you think about how we make a prediction of this entire thing, we'll have to actually first start with the building of electronic structure diagram and understand the energy difference and zero field splitting and calculating all these rates, and then you calculate this kinetic equation. On top of that, the ODM, so-called ODM, didn't write it down, readout also apply microwave, where we'll rotate the occupation between the ms0 and the ms plus minus 1. I'm not talking about that. That's another type of readout. It's looking at the occupation difference with and without microwave. So this is a picture of contrast of diamond. So in this picture, we give the percentage, and this is actually more complicated than this one. On top of this picture, what I mentioned about the difference between ms state, in this picture, we also apply a magnetic field. And each magnetic field will obtain a different contrast. And on another complication with the actual measurement, as I mentioned, this contrast is mirroring with and without microwave, which involved the optical spin state rotation. So you can see when you increase the magnetic field, the contrast are going down to 0, and what happens is you are closing the difference between ms0 and plus minus 1, because this is effectively a Zeeman terms tuning of the energy levels. So okay, so this is a long discussion of how epicenter works. Theoretically, we will have to do our calculation start from very beginning. So we call that being first principle, is because we do calculations start from atomic structure and using quantum mechanics only, and we don't use experimental parameter. So to be said, you will have to start with a structure is stable at the temperature you are operating with whatever defect you are interested. And then you look, do I have a two-level system? Because this diagram of NV center start with a two-level system. In fact, it's a three-level system. This is just two-level. You can think of this our two-level triplet-to-triplet transition. In fact, if you do ODMR or you want optical contrast, you need some intermediate state. But that's other stories. So after you have the basic electronic structure, and then you will have to thinking about the optical interface I mentioned earlier, bottom spin optical interface. We do a lot in our work. This process is actually even more complicated than I just mentioned, because even your spin state is initialized even before you optically excited, they can also relax. So this optical process is competing with some of the spin process. The spin also relax because there's a spin orbit and there's a phonon coupling at the final temperature. There's a spin-spin interaction. So there are a lot of process going on at the same time in this spin optical interface. And this need to be predicted, and on the top of that is what kind of optical signature you can exactly measure. For example, photoluminance. Photoluminance is a signature of different defect center. Like NV center has its very signature photoluminance of, let's say, PL line shape. What I will mention a bit later, we will have a specific ZPL position with a very sharp peak. You hope it's a sharp peak. If your defect is not good, then this ZPL may be even invisible. Then you basically are not able to identify what is it called, that zero phonon line. That's not a good qubit. And this broader part is so-called phonon line shape. We can calculate. This is the effect of electron-phonon coupling. If your qubit is strongly coupled with lattice vibration, you will have this very broad feature. And that is a fingerprint of your defect as well. Experimentally, we can measure it, or we calculate it, and then you compare, and it's matched, and then you say you get this defect. And on top of that, you can calculate in the lifetime of the spin T1 and T2, because these, as I said, competing with this optical radar process. A lot of times underlying people think the T1 and T2 be long enough, and then you can have many optical cycles in between. But it depends. If you're looking at the room temperature, the T1 time can be quite long. So this process actually pretty complicated. We do in our group. Probably I will not get to this in detail today. You will often start with spin Hamiltonian, because you're doing localized spin. We can start with a spin Hamiltonian with different spin-spin interaction and spin-orbit interaction. And then you apply perturbation, either a magnetic field or coupling with the phonons. And you can compute the matrix element based on perturbation theory, and you can construct a grid equation for T1 and T2. We have a different theory to do that. We develop quantum dynamics theory to compute T1 and T2, which go beyond simple grid equation. Not right now too much. So that comes down to how do we do in the computation front. I mentioned a lot of background. So in fact, if we want to predict any of these, we rely on reliable electronic structure theory to start with. this, what I say, electronic structure theory, is a theory can predict the energy levels of the electrons. This theory can help you predict the ground state structure to begin with. Do you have a C3b symmetry or you have a CS symmetry? That will give you a very different selection rule. To predict the structure, you will want to predict also spin properties. For example, nuclear spin, electron spin interaction. We can calculate the hyperfine parameters. We can calculate the so-called zero field splitting with the different MS sublevels and energy difference that's due to spin-spin interaction of two electrons in the NV center, and spin lifetime. And other property I mentioned, steady state dynamics and the spectroscopy, electron-phonon coupling. There's a lot of discussion on electron-phonon coupling in the spin qubit community, because ideally you don't want a strong coupling with phonon. Because those phonon actually will first make the PL very broad and invisible, and those phonon has also caused the T1 lifetime being too short. And the driving force for all these calculations, there are many levels of electronic structure theory, but in category, often we start with mean field level theory, with effective exchange correlation or effective many-body interaction is exchange correlation potential, so-called density functional theory. So this is a theory all the ab initial calculations start with. We can say DFT is not an accurate theory to predict spectroscopy results. But this is often where to start with. This method is the foundation of a lot of these other methods. For example, if you want to do including many body effects, like the electron-electron correlation, as I mentioned later, with the GW Bethe-Spitzer equation, this needs to build on top of density functional theory. So density functional theory wave functions are using as orbital as inputs to build up with the so-called self-energy operator and build up the correlation function. The same as time-dependent density functional theory. This is also a theory because include the electron-electron interaction more accurately for excited state. But you do have to start with DFT as initial inputs. There are other theories mentioned briefly later, quantum embedding theory and wave function quantum chemistry methods. For example, couple cluster or configuration interaction. So sometimes when we have a new system, if we don't know exactly what kind of correlation situational system is, you want to start with a relatively accurate method which can set up a reference for you, that you can see whether other approximation works, and then we have the down the line, those are more accurate methods. I'm just going to tell you a little bit of what I mean of this terminology. If you start with a quantum mechanics class, you have not really encountered all the terminology. So, as I mentioned, first principles, we need to solve electronic structure and nuclear movement from quantum mechanics with appropriate level of approximation. So, a lot of times, underlying, we already make approximations for the electron-ion coupling. To think about if you have more than one nuclei, for example, H2 or more complicated molecules, you will have to solve in principle, you have to solve the electron nuclei at the same footing. But To make it simpler, we often use so-called Bohr-Oppenheimer approximation, which you can consider the electron moves so fast and the nuclei is being fixed when the electron is moving, whereas the electron is moving spontaneously with the nuclei. So with that approximation, we can look at the electronic structure at a fixed atom position. And that is the type of theory I'm read underneath. If we consider the atoms, electron-ion interaction as Bohr-Oppenheimer approximations, we can solve the electronic degree of freedom with either so-called near-field level theory, for example, Hartree-Fock approximation, where the electron-electron interaction in an averaged way, you can consider all the other electrons smeared out like a cloud as the electron density interact with your electrons, where you consider being the object. At the end of, you sum up all the energy of each electrons. This is just a very rough description. Of course, underlying there's a subtlety. For example, density functional theory, it does have exchange correlation potential, which taking effectively many-body effects beyond this simple picture. But if you're not happy about this level theory, and often we know this level is not good enough for excited state, and you do the beyond mean field theory, that's what I'm drawing, you take into account the correlation between the electrons. Which is, if one electron, this electron moves closer to this electron, and this electron will be repulsed to other place. So it's a very complicated many-body problem. You can't really solve it exactly. That's what I meant. You have a different level theory you can pick. But they have their pros and cons. There's not really a single theory work for everything. Especially for defect. It's a very difficult problem. You are doing solid state with delocalized electrons in the environment. But you also have a localized defect. I need to treat the defect often differently from what happened in the environment. It's a very complex, that's why the theory for spin qubits of quantum defects are still developing these days. So today I'm going to give you a flavor of the electronic structure method, what we do in my group for electron-optical properties. So this type of method is very general. It's good for most semiconductors. If you want to do not only defects, say if you want to do the optical properties of HBN, TMDs, and most semiconductors, they work very well. I'll show you a diagram later. So I start with a picture of photo emission spectrum. As we are talking about electronic structure, and this need to relate to observable. So the photo emission spectrum energy related to either you kick out the electron from the occupied bands or any electron to the conduction bands. And the energy of kicking out an electron from the highest occupied, this is the first ionization energy, or any electron to the conduction band is the electron affinity. And the energy difference between the two give you the band gap, is the photo emission gap, which you measure in the photo emission spectrum. And we often calculate this with so-called GW approximation, and it gives very good band gap for semiconductors or wide band gap insulators. But if you do optical property, there's another level of complexity. The picture is often you have photon in, you have a neutral excitation, exciting the electron from valence to conduction. And this electron, which is the red dot, interact with the hole which is left behind. where originally was occupied, these two still interact in your system. The electron didn't get out. And because of their interaction, it formed a bound exciton. And the first excitation energy or first exciton energy we often refer to the optical gap. And the difference between the photon emission gap and optical gap is the exciton binding energy that I wrote here. So that makes the difference. If you're looking at the difference between the optical gap and photon emission gap in 2D materials, they can be very large. It can be 0.5 electron volt or up. And the right-hand side, in order to take into account this type of electron-hole interaction, which is pretty common in 2D materials or even spin defect. Because the spin defect is working with very localized electron holes. They have very large actual binding energy for the defect center. There's always like defect bind exciton in the spectrum signature. So for this type of picture, we do the Badger-Spider equation. I'll tell you more what I mean, but it's dealing with two-particle correlation function. Maybe I should have just copied them. I don't know, did you guys have questions, just feel free to interrupt me. So if you have first the quantum mechanical class, this is the time-independent Schrödinger equation. For single electrons, in the density functional theory, it's more approximate. In more approximate in a way, you still have approximate, you have kinetic energy operator. This is no difference from any context of Hamiltonian. And you have the potential energy for different contributions. So this Hartree part is the classical electron-electron interaction. It's there even without applying quantum mechanical concept. And this is the external potential. This is electron-ion interaction or other external potential. And you have this also extrinsic correlation potential. If you do any kind of density functional theory, you have to pick this extrinsic correlation potential. You heard about local density approximation and generalized gradient approximation. This is all about how we get a good approximation of this potential. And this potential, in fact, is the difference between the correlated picture, this correlated picture, and this mean field picture. In theory, the difference between the two is your extrinsic correlation potential. Of course, this is never exact. Often, you pick one based on certain condition. There's a so-called Koopman compliant hybrid functional, or they are functional condition can define this extrinsic correlation. And the phi is your wave function is the eigenvectors of this Schrödinger equation, and epsilon is the eigenvalue spectrum. So this gives you one electron energy. So that's different from the energy of the entire electronic structure, many electron state. This is a single electron, which gives you the photon emission, what I mentioned. And the solution of this equation gives you reasonably good charge density and good ground state energy and property related to ground state energy. For example, lattice vibration. If you want to calculate phonon property of the system, DFT does a reasonably good job. Or predict the structure property, lattice constant. These are all okay because this theory give you, in theory, give you accurate charge density. For the optical property in the spin qubit community, we do a lot of excited state to start with. Then we have to do the beyond DFT. And that's what I mentioned earlier. We have to deal with either the single particle, one particle picture or two particle picture. So in this context, the first thing we can improve is to include the effect of screening when we deal with electron-electron interaction. So that's what I said. I'm going to change the picture. Instead of deal with electron-electron interactions, a very Coulomb interaction, we consider electron-electron interaction as a screened Coulomb interaction. And this screening is so important. This screening takes into account the effect of all the other electrons around. And then you can effectively consider this electron-electron interaction is screened by other electrons, and it becomes weaker. And this screening is the dielectric matrix. And if you take microscopic limit, it gives you the dielectric function you can actually measure. This dielectric matrix contains all the local field information, the resolution of the atom bonding. So this dielectric matrix, in the denominator of your 1/r Coulomb interaction, gives you the screened Coulomb interaction. You can think of as simple as 1 divided by epsilon time r. And with such simple concept of including screening, we can build the so-called GW approximation. The G is the one particle Green's function, and W is the screened Coulomb interaction. And this simple convolution gives you so-called the GW self-energy. So this self-energy operator will substitute where was the exchange correlation potential in your DFT Hamiltonian, and then you can solve this eigenvalue problem. But in this condition, because your self-energy has energy dependence, it's non-local, this solution of epsilon is going to be complex, because your Hamiltonian is non-Hermitian. And the complex eigenvalue has its use, because the imaginary part of this complex value corresponding to the lifetime of the state. So you have a natural broadening of the state when you solve this. So in the past, some years ago, I was working on this theory with my previous advisor. Start with building up dielectric matrix efficiently. If you do things in the traditional way, you have to calculate the dielectric matrix in this very lengthy equation, which you have to calculate each matrix element on a grid of plane waves. And the V and C corresponding to conduction and valence. You call it, the K is your K one in the wave vector in the first Brillouin zone, and the Q is the momentum transfer. But anyway, so you will have to calculate this matrix element, you have to calculate this energy difference between pair of states and sum them up and divided by the 1/q plus g squared. So this calculation actually is very demanding because you have sum up all these bands. Instead of doing this lengthy calculation, we had a smart way of calculating dielectric matrix by a iterative procedure based on the density functional perturbation theory, where we set it underneath. So effectively, we are using perturbation theory, calculating the response of external potential. We are calculating only a few eigenvectors of the dielectric matrix. So this eigenvector of U can be calculated with the density functional perturbation theory. And you rebuild this dielectric matrix with such a form. This is a simple concept of eigenvalue decomposition numerically. The saving is, if you look at the spectrum of the epsilon, it converges with the eigenvalue very fast. So we don't have to compute a lot of eigenvectors. We just need a field to rebuild it, and then you can use it as input of the screening for the screen pulling potential, and then you can build up the self-energy, and you go and solve your GW problem. So this has advantage of avoiding the summation of the states. There's a lot of numerical advantage, and that this theory actually built up for the past 15 years with many people's effort. I'm not going too much in detail. I'm just going to show with that kind of theory what you can do. You can first get the band gap in much better agreement with experiment. This is experiment. This is calculate band gap of the system with band gap between less than 1 electron volt to like 8 electron volt. Many systems compare with what you get from DFT, which is a red dot. This is green. This is blue. Green dot is much better aligned. If you do band gap of DFT, it can be over 50% error. That's not surprising. But since we're doing optical property, the band gap is an important parameter. And in the past, we have looked at, for example, 2D materials, multi-layer 2D materials. Each being is a good host of spin qubits because it has very wide band gap. And the environment is relatively inert, and they can have a nice two-level system. And it's very easy to probe experimentally. So we calculate the GW band gap, and we compare it with other theories with different functional. In order to develop a relatively cheap method, we also developed this Koopman-compliant hybrid functional, which has reasonable agreement with GW. Underlying is the saving of this PBE0 alpha is we don't have to calculate the screening. We just need to calculating fork exchange. It's a level cost of Hartree fork, which is one of the simplest DFT method. So it's for the purpose of larger scale calculation. Anyway, so that's past work we were using this, applying this GW approximation for interfaces and defects in particular for 2D and 3D systems. So why defect calculation is expensive? If you think of, we are looking at an isolated impurity in the environment. And this environment needs to be large enough your isolated impurity is actually isolated. You don't want this impurity talk to your other impurity, because we always have periodic boundary condition for solid state. Always. We have a box, there's a periodic boundary condition. And because of that, you can never say there's no interaction with the periodic image. That's why we need to always build a big box. And this impurity in the box needs to be separate enough from the neighbors. At least their wave function should not overlap with the neighbors. So that causes the calculation of the defect goes much faster. Like, the cost is usually n power 3 to n power 4, n is number of electrons. For a defect calculation, even n is center being the simplest one, you need the order of 2,000 electrons to start with. So it's very difficult, and we need to have scalable theory. That's why there's a lot of electronic structure method development. First, there's other theory. GW is one of the cheap correlated methods. If you do quantum Monte Carlo, and that will grow even faster, the cost will grow much faster with number of electrons. Okay, so we talk about the band gap, which simplest parameter for semiconductors, and how we do the optical property. So first I introduce how we do the particle excitation. We start with the quantum Liouvillean equation, which is a time-dependent form of evolution of density matrix, and you can build your density matrix with wave function input, product of R and R prime. And in your density, in your Euclidean equations, your Hamiltonian contains the different terms we wrote before. Even the DFT has these three terms. An additional term of the self-energy operator. So this is the operator we wrote already when we write the equation for GW approximation. And for the commonly used Badger-Spitter equation, we are not exactly using the GW self-energy. We are using often using a statically screened self-energy, where this spring-Coulomb interaction is actually has no frequency dependence. You can choose to have frequency dependence, but the past benchmark shows to have frequency dependence in the spring-Coulomb interaction was useful for only certain cases, for example, plasmas. Not going through detail, so this is one way to solve so-called the Badger-Spitter equation, and in fact this part contains the electron-hole interaction. And what actually doing from here to the final observable will be your optical spectrum. For example, dielectric function was a frequency. You have to go through calculating time-dependent rho, and then you're calculating time-dependent polarization, and then you do Fourier transform. So I'm saving those steps. I'm just telling you the basic concept. At the end, you'll have the response function, and this response function is basically the response of applied external field. For example, a photon per source, and you look at the response of the system. And this function connects the applied perturbation and the response. And what we look at, this epsilon 2 is a so-called absorption spectrum. This is the imaginary part of the dielectric function. And we compare, for example, both silicon and constant oxide between the theory and experiment. Experimentally, there are always additional features. For example, this experiment actually has a tail close to 0. So sometimes when we see this feature, we have to interpret what happened. Because this is actually a metallic response feature. This is showing this system has some doping. In fact, this system has some sodium doping to give this response. Otherwise, it's going to be gapped. We know this system is supposed to be gapped. So compare with the experiment needs additional interpretation sometimes. And we compare with the experiment optical gap. So there's experimental 1s and 2s peak position. So this 1s is the first axial peak position, as 2s is the second axial peak position. We compare as a function of number of layers for WS2. So we can see the nice agreement between theory and experiment. The theory is the dot and the experiment is the triangle. And in the meantime, we also have this cross. So this cross is your photo emission band gap. And the difference between the cross and the dot is your absolute binding energy. You can see this binding energy being really large for this 2D material. But it decrease, this difference decrease as a function of number of layers. Because you have more materials, when you have more layers of material, the screening increases. And because the screening is in the denominator for the spring-Coulomb potential, the electron-hole interaction becomes weaker. So you have a monotonic trend. This is expected. But if you see the 1s and 2s, they behave very different. The 1s position is relatively stable, but 2s has actually a change. So the cancellation is not complete between the change of the band gap and the change of the external binding energy. Anyway, so what we benchmarked in the past, we benchmarked a lot of host materials like semiconductors, 2D materials, and HBN. So this is the exciton band structure. It's different from the conventional band structure because this actually shows this. It shows the exciton energy. For example, for this one, the lowest exciton energy is around 5.2, and it's off gamma. It's actually at a large momentum. It's useful information for people want to look at excitonic features or the lifetime of excitons, which we do as well. So this is not defect calculation, but if you can do electronic structure right for host materials, the assumption is you will be able to get the defect property more accurate as well. But that needs to be validated. So at this point, I introduced the property for calculating band structure and property a theory for calculating optical property. And this type of optical spectrum, they are useful for identifying what materials you have. For example, for defects, those are also signature necessary to identify for different defects. So on top of that, there are other theories, especially if we have a defect in an environment of solid, when this defect is quite different from the environment. We would think we need to have defect treated in a better level theory than the environment. So that's where so-called embedding theory comes from, where you actually embedding the active space in the environment. And this is picked up not by real space. This is picked up by the type of states or energy range. You can define, say, you have 60 orbitals in the defect related to the defect centers, and those you are considering the states you need to treat accurately. You can use exact diagonalization or full CI, and they basically need to map on an effective Hamiltonian. And the environment, you treat it at a lower level theory, for example, square-Coulomb interaction with a GW approximation. That's a often used approach in the defect community. In this case, our potential is using the information we build from the square-Coulomb interaction. There are a lot of technical details I cannot really go through. What I want to show you here is a comparison for NV center. So the quantum embedding theory compared with the experiment, you can show a much better agreement with the experiment than GW. But the GW BSE is in good agreement with the experiment for the triplet state, but for the singlet state, it's much worse. And there's a reason for that. The reason for that is the singlet excited state. They are so-called multi-reference state. So those states fundamentally require more than one Slater determinant. So that's so-called static correlation. That is not something you can do with many-body perturbation theory, which is built on theory from one Slater determinant. So this is a well-known problem for the open-shell singlet state in this community, and that's why we actually keep on developing other theory. Quantum embedding is one type, or also we are looking at quantum chemistry methods to solve this type of problem. Okay, so these are actually a lot of details. If you are interested in electronic structure, I can tell you more about what are all these terms. So now I get to think how much time we have.
I would say
10 minutes?
yeah. I mean, we have about half an hour including questions.
Okay. Yes. Yeah, I'm just talking myself all the time. So let's look at something a bit practical. As before, I was mostly showing the different flavor of electronic structure and what do they do. Practically, we start from looking at what are the possible material candidates. You need to pick the host material, and you need to pick what the defect in the host material as the qubit. So 2D material is one group of material quite popular in the past 5 years. One of the most popular is boron nitride. Yeah, you can find quite a bit of experimental discussion on that, how you look at the point defect in HBN for different applications. And people have found the defect has magnetic field response. Some advantage of this type of material, it has large band gap, and it's easy to integrate to devices, and easy to manipulate. Or accessible for defect manipulation by STM, for example. But there are a lot of difficulties in terms of theoretical prediction. This type of defect not only need to take into account the correlation effect I mentioned before, you have to worry about substrate, you have to worry about the isotropic screening. A lot to think about, and experimentally it's not yet confirmed which one is the best one to work with in terms of the defect in material. As I mentioned, when we have the defect in these 2D layers, if we think about the electron-electron interaction, they are more screened in the layer, but they are not screened in the vacuum. The dielectric constant of the environment is one, is vacuum. So the interaction between electron hole pairs and defects is very strong. And you have all these processes you need to worry about. You need to worry about the defect exciton interactions and exciton phonon interactions. So all the interactions become stronger. So from a theoretical point of view, we need to have reliable theory to start with. We have worked on this in the past, about from 2017, we started to work on this type of problem to build the electronic structure for defects in 2D material at many-body perturbation theory level, as I mentioned earlier. And we developed charge correction. So this reason we say about the charge cell corrections. So think about if you have impurity in the cell, and this impurity actually has additional electron, like NV center has negative charge. This additional electron interact with the image much stronger than the neutral in species, because it's a monopole, and the dies really slow. So you have to have a theory which can correct this type of interaction. We developed for 2D, then we can avoid very painful supercell extrapolation. And then, if we want to do the optical property I mentioned, then you will have to calculating radiative process where you have a photon out, and we build the rate equation with the Fermi's golden rule. And the basic structure, you have a matrix element for the dipole. This is kind of think of being an exciton dipole, and energy conservation between the electronic states and the photon. And non-radiative process, and effectively you have to consider a phonon-assisted electron-hole recombination, where your matrix element contains the electron-phonon interaction. So first of these, you have to divide it, and then you have to approximate to a form you can calculate effectively. This actually is the approximate equation with so-called static coupling approximation. Then inter-system processing. This inter-system processing is what I told you exactly before from the triplet to singlet transition. And there you have to worry about electron-phonon interaction. So this phi is the phonon wave function. On top of that, you have a spin-orbit coupling lambda. So this process happened when they have this optical this is a non-radiative transition. Transition from the triplet to singlet due to assistance of the phonon. At the same time, the spin flip from triplet to singlet state. This flip is due to spin orbit. And substrate effect and quantum embedding theory I mentioned before, 2D defects. So these theories are all necessary as fundamental tools we use for looking at the spin defects properties. So there are another set of tools I did not mention here is related to spin lifetime calculation. We also build tools to look at the how spin relaxes in different pathways due to nuclear spin, due to phonon coupling, spin orbit. Not to talk too much today. Okay, so I will go relatively quick on this benchmark of different observables. One is related to the lifetime of a recombination. So when you generate electron-hole pairs, like I said, in this optical radar process, you have a photon in, an electron excited from valence to conduction. You have an exciton, and this exciton is not going to stay there forever, and we not assume it will stay there forever. I mean, there's a finite lifetime for the electron-hole recombine, and go back to the triplet ground state. So this lifetime needs to be computed as a part of input for the optical radar. And we calculate from solving the better speeder equation first, get the energy and the dipole moment for the exciton, and input here, this EQ is the exciton energy, and the Q is the exciton momentum. And this is simply a thermal average, because at the end we want to have a finite temperature lifetime, where we get compare the exciton lifetime between different material. So in the same, for the WS2 is pretty close. For the BP is the black phosphorus, we have 2-time difference. And we also benchmarked phonon-assisted exciton recombination. So this is the type, not just direct electron-hole recombine photon out. And this is the type you actually have additional phonon participate in this process when you have photon out. And calculate this lifetime with many-body perturbating theory as inputs at finite temperature. So more details you can look at the archive paper. A non-radiative process. This is a little bit more complicated. The one complication of the non-radiative process is imagine you have electron-hole excited, a pair with say 0.5 or more electron-hole difference. And this recombination is all through phonon, and one phonon energy is only tens of million electron volts. So based on the conservation of the energy of electron-hole energy difference and the phonon energy difference, phonon energy, you naturally have a multi-phonon process to start with. And this is very hard to do exactly. In order to do that, in the past year, this is more than 10 years effort how people can approximate the electron-phonon matrix elements. It's basically the coupling between these two states, which this broad curve is the electronic state, and on top of that you have these vibrational states, so together called the vibronic state. This vibronic state, IN coupled with Fn, and how this coupling matrix element can be calculated as It's a long effort. I'm not going through the detail how this is derived. The end result is this equation, which we have shown is actually work very well for defects in gallium nitride and HBN, where it contains a so-called electronic term. This phi is an electronic wave function, and this is a first order derivative of a collective variable Q. This collective variable is defined in this diagram of extrapolated the variable from the initial structure to the final structure in a one-dimensional coordinate. And you can calculate this at a fixed position R, and the phonon part has the phonon wave function, and here just approximate with harmonic oscillator wave function, and the displacement of the Q, along the one-dimensional coordinate pathway. And this equation effectively takes into account the multi-phonon process, because the phonon difference can be large. So we have implemented the benchmark for 2D and 3D system. For defects particular, this theory actually works much better for defects than bulk property. As an example, how we are going to find a new defect. So this is the research start. See, either you be a developer in my group, you develop theory and implement codes, new functionality, or you do applications and you find new defects. The new defect design often goes through the process of manifolds. Start one with a structure. So structure, you think of what kind of element you want to put in, for example, HBN host. You have a periodic table to choose, and on top of that, you can choose different positions, being substitutional, interstitial. On top of that, you can have complex with a vacancy around it. You have a substitution plus a vacancy, like NV center. So we start with a model of NV center like defect. We're using this MO substitution of boron plus a vacancy. After relax, this is its structure. This is its equilibrium structure at the ground state. And with that defect system, then you're calculating the defect formation energy. So the y-axis shows you how much energy it costs to form the defect. It looks like a very large energy scale, several electron volts, but in fact this can be realized. Even in this center, the defect formation energy was at oxygen, certain oxygen poor condition, I don't remember exactly, was also this order of magnitude. So one important thing is you want to see which charge state your system is preferred at a different Fermi level. For example, if your system is preferred to be close to intrinsic, your Fermi level is close to the middle of the gap, then you see whether your neutral state is being stable. For this system, the neutral state is the lowest energy in this range of Fermi level. But if you're close to the conduction band, this defect diagram shows you would prefer to be -1 charge state. How to calculate this diagram is very fundamental in the defect physics. You have to calculate the formation energy of the defect at a different charge state. You plot it on this scale with the Fermi level moving from valence to conduction band. And then you look at which charge state has the minimal energy. It tells you which charge state is stable. And the y-axis tells you how much energy costs to form it. This can translate to the defect concentration. For example, the bottom I shows with a diagram on the top, similar for hematite, we can calculate the defect concentration as a function of synthesis temperature. And this is something useful for experiment. And you can tell them at what synthesis temperature you will get roughly what defect concentration, and at which, in this case, we show this one defect was preferred in the higher synthesis temperature, the ionized tissue. As example, I also want to show if you finish the defect prediction of the formation energy being stable, then you can look at the optical property. We see, okay, we have a bright transition. Optically, using photon, we can read the photon out. And then we can look at the ODMR. So this is not yet ODMR. This is the diagram, as I showed you earlier, similar to NV center, where you have zero field splitting in the ground state, zero field splitting in the excited state, and you have intersystem crossing and recombination. And all these processes are needed as input for spin-dependent PL contrast optical readout. So, okay, so I'm not going through detail of this one. This is HBN's carbon defect, where we actually compare it with the experiment for the carbon defect. First, the PL is very much in agreement with the experiment between theory. And we also compare different parameters of photoluminescence lifetime. This parameter is complicated. When they get this, actually contains both radiative and non-radiative process. We have to calculate them both and sum them up and give you the lifetime. And we can see how that compares with theory. And so this is our theory calculation give you. Okay, this is here. 2.19 nanosecond, and experiment is this range. And we also calculate ZPL and Horner's factor. The ZPL is also in reasonable agreement with experiment. Experiment is always a range, because each defect is not identical. So in this case, the carbon dimer is not used as a qubit. It's only used as a single photon emitter. Based on this property, when your quantum yield is not low, like tens of percent, it's actually considered pretty high. And ZPL is within 2 electron volt, is actually considered reasonably good as a photon emitter to start with. Even it doesn't have triplet ground state, you can use it for different purposes, for photonics. Other thing we look at is we look at the effect of the strain. This will show how this optical property change. This can be compared with experiment. Optical spectrum or lifetime, radiative or non-radiative lifetime can be compared to experiment. And we look at the substrate effect if you put a HBN on black phosphorus. Their lattice is totally different. If you build a atomic structure of these two, it's very difficult. So we use the effective summation of the polarizability method to avoid have to build this supercell of these two materials together. To avoid the superficial lattice strain. And we look at when you have different substrate, how the binding energy of acetone change and GW gap change. So with all of this information as input, we calculating what input as ODNR. So this is a very complicated project. This actually already published, where we basically calculate all the rays in this diagram, and then we look at the excited state population change as a function of time for all the different states. And we look at the difference without and with microwave. As I mentioned, when you have the microwave rotating the state, it's going to change the population between 0 plus minus 1. And it will finally change the steady state population of different states. And this difference with and without microwave give you this steady state PL intensity with and without microwave. And that is the contrast. This is the steady state contrast, which was different from what I mentioned earlier in terms of the transient PL contrast. And also, your experiment will mirror as a functional magnetic field, which shows a quenched under magnetic field. This curve can be different between different effects. Sometimes the contrast will be positive and negative. Sometimes this curve can be a different shape. That's also useful. I think I will skip some of these details. So that's what I was hoping to show you a little bit of the complexity of spin-orbit coupling in this context. But maybe more useful is telling you guys a little bit of so-called dynamical Young-Taylor. So when you have a defect at the excited state, after you excite it, so it initially kept the same structure as the excited state, but it can relax. And if your broken symmetry structure is a lower energy, it will relax to a broken symmetry structure. For example, in this center, it has this dynamical Young-Taylor. Actually, the lower energy is these three petals, which are the CS symmetry. It's a lower energy than the high symmetric C3b structure. And because of broken symmetry, then the intersystem crossing between this state and the singlet state is allowed. I'm just telling you a picture. What I show here, if you have the dynamical Young-Taylor which give you a CS to the C3b ground state transition, this transition become allowed compared with if it's an original C3b to C3b transition, singlet to triplet transition. How I know that? Just by simply calculating the risk, I know this is much faster than this, and just by looking at the potential energy diagram, you can also show if you have the broken symmetry structure is a barrier of happening between the state crossing barrier is much smaller for this one than this one. So all I'm trying to say is this complexity of this broken symmetry is physical, is important, is actually critical for NV center. And that happened that for a lot of defects, this spontaneous symmetry broken happening in the excited state, and you have to take into account this complexity and additionally good treatment of electronic structure to get the rates in agreement with the experiment. So that's what I show you at the end. If you take into account properly the dynamical Young-Taylor for electron-phonon coupling and calculating spin-orbit coupling at the right level of theory, taking into account multi-reference states of that, and then finally you can get the rates. And these rates are being the input of the ODMR contrast. And experimentally, actually, when they do this measurement of contrast, they rotate their magnetic field. That's another useful thing to look at, is this magnetic field angle dependence. We can tell them which direction of the magnetic field you are going to see the highest contrast. For example, different field direction aligned to the defect give you very different signature. This is the good input for experiments as well. Okay, so I think I will just stop here. I mentioned quite a long story of how do we look at the optical property of the spin qubits and what are the important parameters to calculate, and all the complexity from the electronic structure to begin with. And I mentioned there are a lot of room in this field to further develop accurate electronic structure theory for spin defects, and also a lot of room to look at the dynamics of spin and electrons. Okay, I'll just stop here.
one.
Yeah.
So it seems like when we talk about this ODMR and defects in HBM, wondering like what's a fundamental limitation to explore like spin qubit or similar property in other TNDs. To my knowledge, I think certain like TNDs, they are actually very bright for isotons. And
There's no fundamental limitation.
yeah,
So
then why most of the study seems to focus on HBM for
Yeah.
2D material?
So that comes down to the criteria of what is the host, good host material. One thing with TMD is the gap is a little small. So you cannot really avoid the entanglement with the bulk states. So those bulk states often hybridize with the defect states optically, because the binding energies of the exciton of the bulk is large. And this hybridization causes decoherence. And you don't want that. You want the two-level system being perfectly isolated, ideally being perfectly isolated.
So it just sounds like searching for more large gap semiconductor in 2D material.
To start with.
Yes.
I think there are some large band gap 2D material to start with. HBN just being the easiest one. But HBN is not so good actually, because the nuclear spin concentration is too high. That's why it's not used still. So you want the wide band gap and the nuclear spin concentration being low to start with, and then you look for some defects which has the right property like the eccentric. Yeah. So I would say that because the parameters we are requesting is a large number, then it really narrowed down not many good candidates.
I can have a quick question. Still have 2 minutes. You quickly mentioned that to describe this accurately, you need, at least in some cases, more than one Slater determinant. And shortly after, you discussed, you had actually a slide in which you had various approaches, including also maybe in the future quantum computing as a resource. So that can you briefly elaborate, given that this is a quantum school?
Yeah. So there is a lot of application for the quantum embedding theory type. So the part of treating of the active space and using the full CI solution, there's a efficient way of doing it using by taking the notation of quantum computers. This actually has been tested by a few groups, and there's different front of development. Either you develop this theory in terms of how you do the effective Hamiltonian, calculating the screening more efficiently. There's also how you apply this quantum computer selection of the algorithm more efficiently. To have this, you can have a solution of a larger active space which converges the calculation properly. Yeah.
Recording stopped.
So, okay, thank you. Given that the recording is stopped, maybe this is a sign. So let's
Recording in progress.
okay, let's start over again. So let's start Yuan again. Let's thank Yuan again. For a very nice talk. And Tianqing will take over for the lab tour.
Yes, it's a real stop.
Recording stopped.
Okay.
Great.